So we're wanting to know, when is this function greater than 0? So the left side of the equation is the function, and this entire inequality is a statement about that function. We want to find what values of x cause the statement to be true. So that's what it means to solve really any mathematical statement is. You want to find what values of the variable, in this case x, cause the statement to be true. And so here we have x minus 8 times x plus 5. And we want to look at the zeros of the function. And the reason is because those are the points where the function changes from either positive to negative or negative to positive. Let's just take a look at a graph of this function. And again, when I say function, I mean the left side of the equation. That's the function. The entire inequality is a statement about that function. So going to Desmos, wait a second here. There we go. That's better. And I type in the function. I can type it as y equal, or I can just type it as an expression, and it will graph it either way. So it's a quadratic function. Let me zoom out a little bit so we can see. And you can see here, this is one of the x-intercepts right there, -5, 0. So -5 is a 0. And then also 8 is a 0. So if we go from left to right, this function starts out above the x-axis, so therefore it's positive, and then on the x-axis the function is 0, and then it goes negative. After we pass -5, it stays negative until we reach x equal 8. And then it's equal to 0 at that point, and then it becomes positive again. And so to the left, in other words, from -infinity to -5, it's positive. And then to the right of 8, from 8 to infinity, it's positive. And you will recall the question was, when is this function greater than 0? Now I showed you a graph of how to determine that, but let's suppose we didn't have the graph. How would you solve this problem? Well, the first step one of these problems is to bring everything over to the left. And you want 0 on the right. Then the step 2 is find the zeros of the function. So we do, in this particular example, we set the function equal to 0 and solve for x, and that will allow us to find the zeros. So if you have a product like this equal to 0, then each factor could be 0. So we have x minus 8 equal to 0, or x plus 5 is equal to 0. And solving those equations, we add 8 to both sides here. And then we subtract 5 from both sides. And we get x is equal to 8, or x is equal to -5. So then the next step, step 3, is to plot the zeros on the number line. So I draw a number line, and we have -5 on the left and 8 on the right. And because these are zeros and this is a polynomial, the point at which it crosses the x-axis is where it changes sign. So everywhere on this region, this interval here, it's either positive or negative. Then it changes sign at this 0 here, and it's either positive or negative in the entire interval. And then it changes sign again, and it's either positive or 0. So we're looking at when is it positive, when is it negative. So you test the regions. Now we already know the answer because we saw the graph, right? But let me just pretend I didn't see the graph. So I'm going to test these regions, and I'm going to pick test points. All I have to do is pick one point, because I know if it's true for that one point, it's true for everything. And I'm just checking the sign of the function. Is it positive or negative? So I'm going to pick -6. And here between this negative number and this positive number, I always like to pick 0 because it's easy to calculate with. And then here I'm going to pick 9. So these are test points. And I'm going to plug them into my original function. So I plug in -6, and then -6 minus 8, that's going to be negative. -6 plus 5 is also negative. So I have a negative times a negative, that's a positive. So we want to know, when is the function positive, right? When is this function positive? So when I plugged in -6, I got a true statement. So it's true. Now, if I plug in 0 here, I get -8. Oh, I'm sorry, I forgot to turn on the... You should have said something. I'm sorry. There it is. My bad. Okay. I forgot to turn on the projector. So plugging in here, we have a 0, and then we have a negative number times a positive. That's negative. And the question is a negative number greater than 0? No, that's false. So this region is going to produce a false statement. Okay. And then here, if we plug in 9, we have 9 minus 8, that's 1. 9 plus 5, that's positive. So we have a positive times a positive. And so for that test point here, we have a true statement. We got a positive number greater than 0. Yes, that's true. So this is going to be true. Okay, see how that works? And to solve an inequality, you want to find what values of x make it true. And if it's true for this point, it's true for the whole interval. Now notice that our inequality is a strict inequality. In other words, it's greater than 0, but not equal. So we're not going to include -5 and 8 because those are zeros, and that the function is equal to 0 at those 2 points. So we're not going to include them. And I use an open parentheses to show that I'm not including -5. And then I use an open parentheses here to show that I'm not including 8. But I want all the other x values where it's true. Okay, so this is the graph. And now if I want to write this in interval notation, so step 4, just to kind of, so you have this for your notes. Step 4 is what I just did, where you test intervals, test or pick test points to determine for which intervals the inequality is true. Okay, so I did that and I shaded in the region. This is the graph. Now to write this in interval notation, this is minus infinity and this is infinity, and you just work from left to right. Minus infinity has always got an open bracket because you can't ever reach negative infinity. It's just an idea. And then we get to -5, but we don't include -5, so we use an open bracket. Then we join it, that's the union symbol, we join it with this interval. So again, we don't include 8, so I'm using an open bracket, and then we go to infinity, not including infinity. So this is the solution set. All right, any questions about this particular example? Let me go back to the graph. And you can see here from negative infinity to -5, it's above the x-axis. And from 8 to infinity, it's above the x-axis, so it's positive. Whenever you're looking at what is happening for a function, in other words, is it positive or negative, you're looking at y values, and y values are vertical, right? So here we see it's above, here we see it's below. Those are y values that we're focusing on. But the solution set, we're looking for x values. The x values are the where the function is doing what it is doing. So here it's positive, and where is it positive? From minus infinity to -5, and over here from 8 to infinity. So the where are x values. And if in my experience in teaching this, a lot of times students have trouble sorting that out. And what I like to think of it is, if your function is above the axis, imagine dropping down a vertical line to the x-axis. It kind of creates a shadow, right? And that shadow, what's underneath, is the kind of the way you locate the function, where the function is above. Okay, kind of like that. I don't know. If you have trouble sorting it out in your mind, just remember y values or function values are what is happening, and where it's happening are your x values. So all of our answers, we're trying to find out where the function is positive. And so those answers are always going to be x intervals. And so they lie on the x-axis. And when I'm doing this testing on the interval, true, false, true, I'm asking the what. So I'm looking at y values, and therefore I take the -6 and I plug it into my function, and that gives me the y value, and then I can analyze, is it true? All right, so this is the what's happening, and then I graph the where. Okay, I hope that helps to keep it straight in your mind. So going back to the assignment, I fill this in. Here's the union symbol right there. And we're going from 8 to infinity. There's the infinity. And then we select the correct graph. Looks like this is the correct one here. From -5, and then there's 8, not including. Okay, solve the polynomial inequality and graph the solution set on the number line. So the first step is to get everything to the left-hand side. That's already been done for us. The next step is to find the zeros. So I set this equal to 0. And then to solve this quadratic equation, I factor. And I set each factor equal to 0. And if I subtract 3 from both sides, I get x equals -3. And here, x plus 1 equals 0. Subtracting 1 from each side, I get x equal -1. The next step then is to plot them on the number line. So I have -1 and -3. And then I want to pick points within the intervals to test the interval to see if it's positive or negative. So I pick -4, -2, 0. Doesn't matter which points I pick, it's just as long as they lie in the interval. So -4, I can plug it into either function. These two functions are the same. So I prefer this one here. -4 plus 3 is -1. -4 plus 1 is -3. I have a double negative, that's positive. A positive number greater than 0, that's true. Plugging in -2. -2 plus 3 is 1. -2 plus 1 is -1. Is -1 greater than 0? No, that's false. And then plugging in 0, I get 3 times 1 is 3 greater than 0, true. And again, because this does not have an equal sign underneath, I'm not going to include -3 and -1 because those cause the function to equal 0, and I'm just interested when is it positive. So I'm going to use the parentheses to show that. And I'm solving, so I want which x values cause it to be true. So that would be this region and this region. And if I write that in interval notation, I'm going from -infinity, and this is infinity, so I have -infinity to -3, not including -3, joined with from -1 to infinity, not including -1. This again is the solution set in interval notation. Okay, any questions on that one?
So you plug the question or the say like -4 or 0 back into the original?
Yeah.
Is that what you do?
Well, yeah, this is just an arbitrary point. I just picked it because I can't test all of the points in here. But what I do know is that if it's true for one point, it's true for all of them, because the sign changes occur at these 2 points, and therefore they're either all positive or all negative on these intervals. So I just pick one point to determine is it positive or negative. And when I plugged in -4, I got -4 plus 3 is -1, -4 plus 1 gives -3, and you got a negative times a negative, that's positive. And that's what I want to know. When is it positive? So it's true. If a positive number is greater than 0, that's true. When I pick -2, I get 1 times -1, that's, yeah. 1 times -1 is -1. Is -1 greater than 0? False. See how that works? Okay. Then I plug in 0. 0 plus 3, that's 3. 0 plus 1 is 1. 3 times 1 is 3. Is 3 greater than 0? True.
Gotcha.
And I'm plugging them in here because this is the same function as this one. I just think it's easier to calculate here. I mean, I could have plugged them in up here as well. And I just want to know if it's true or false. Okay. We'll do a lot of examples today, so you'll start to get the feel for it. It is kind of tricky at first if you've never seen it before. So.
Okay.
And then the graph is right here, looks like. Okay, this time it's x squared minus 8x plus 16. We want to know, when is that less than 0? See, the previous time we were looking at greater than 0. Now we're just switching it a little bit less than 0. So, but the procedure is the same. You want everything on the left. We've got that already set up for us. Then you want to find the zeros. So we set it equal to 0 and factor. That's a perfect square trinomial, right? So if a perfect square is equal to 0, then, well, in this case, x minus 4 has to equal 0. And as it turns out, this 0, which happens to be 4, has multiplicity 2. Okay? So we say that 4 is a 0 of multiplicity 2. We only have one 0, so we just have to test 2 intervals. Okay? So on the left, I'm going to pick 0. And on the right, I'm going to pick 5. And I plug those into my function. Plugging it in here, 0 minus 4, that's negative 4 squared, that's going to be positive 16. Is 16, so in other words, if I plug that 0 in here, you see I get 16 less than 0, right? Because these two terms are going to go away. That's false. 16 is not less than 0. Now I'm going to plug in 5. And it's easier to calculate if I plug in 5 here. But if I plug in 5, either one is going to give me the same answer. When I plug in 5, I get 1 squared. That's 1. Is 1 less than 0? False. And the function itself is equal to 0 at 4 because that's the 0. Well, we don't care if it's equal to 0. We want to know, when is it less than 0. So we're not going to include 4 in our answer. And in fact, it's never true. So the solution set is the empty set. And graphing the empty set is just a blank line. It's just the number line by itself with no shading. Okay. Any questions on this one before I move on to the next problem? Okay. Well, let's just graph it real quick so you can see. We have x squared minus 8x plus 16. And the question is, when is it less than 0? Well, you can see, because this function is entirely above the x-axis and it's equal to 0 at this point, it's never less than 0. If it were less than 0, it would have to dip below the x-axis, but this area is all blank. So to ask the question, when is this function less than 0, the answer is never. No solution. Let's go back to the... Okay, so looking at this problem, we have x squared plus 5x. This time we want to know, when is it greater than or equal to 0? Setting this equal to 0 and then factoring. we see that the zeros are x equals 0 and x equal -5. And then we can plot those. And then we just pick points from each region that we've divided the number line into. So -6, -1, and 1. So here we have, we're plugging in -6. I get -6 squared, that's 36. 5 times -6 is -30. So I'm going to get 36 minus 30 is 6. Is that greater than or equal to 0? True. Plugging in -1. -1 squared is +1. 5 times -1 is -5. So we have 1 minus 5. That's -4. Is that greater than or equal to 0? That's false. Then we pick 1. 1 plus 5 times 1 is 6. Is that greater than or equal to 0? That's true. And because we have, this time we have an inequality that is, you have the chance of equaling 0. So we want to include the zeros because of this equal sign here. We're asking, when is the function greater than or equal? Well, the function is equal to 0 at the zeros. So we're going to include -5 and we're going to include 0. And that's why I'm using square brackets. When you include those points, you use square brackets and then you shade in the area where it's true. And this is the graph of our solution set. And if we write it in interval notation, this is -infinity and this is +infinity. So we go from -infinity to -5, including -5. And then we join that with the interval from 0 to infinity, including 0. So that's why the square brackets. And that's our solution set. Oops. And right here is our solution set, G. So as I told my last class, this is a fairly lengthy assignment. So I'll be very lenient when I grade you for those of you who are Zooming. Of course, if you're in person, you just get full credit for coming and for taking notes and everything. But just so you know, if you don't get all of it, that's okay. I'll be very lenient. I'll probably just give everybody full credit because these problems are kind of lengthy ones. Okay. Let's see here. It's going back to, we have -5x squared minus 5x greater than 0. We want to solve that inequality. So looking for the zeros, I'm going to factor out the -5 and also x. And when I do that, I'm left with x plus 1. So if setting -5x equal to 0 and then x plus 1 equal to 0, Here, dividing out by -5 is just going to give me x equal to 0, and subtracting 1 from both sides, I'm going to get x equal -1. So these are my zeros. Plotting them on the number line, and then I'm going to pick points. I'll pick -2. I'll pick -1/2, and I'll pick 1. So -2, when I square -2, I'm going to get 4. -5 times 4 is -20. Then here I get -5 times -2 is 10. -20 plus 10 is -10. Is that greater than 0? No, that's false. -1/2 squared is 1/4. So this is going to give me -5/4 plus, because I have a -1/2 times a -5, plus 5/2. So -5/4 plus 5/2. Since the denominator is smaller for the 5/2, it's going to be positive because I'm subtracting a smaller number. So I get a positive greater than 0. That's true. Plugging in 1, I get -5 minus 5. That's -10. Is -10 greater than 0? That's false. So because this is a strict inequality, I'm not going to include the endpoints. And this is the true region, so I'm going to shade in the true part, not including -1 and 0, because the function is equal to 0 at those 2 points. And I'm just interested, when is it greater than 0? Strictly greater than. So in interval notation, the solution set is the interval from -1 to 0. And selecting the graph, it's right here. Any questions on that one before I move on? Okay. This time, so far, all our examples were quadratic. This is a cubic polynomial. So in factoring this, I'm going to use what we call factoring by grouping. So let me show you how that works. Because I want to solve, to find the zeros, I want to solve the equation x cubed plus 5x squared minus 25x minus 125 is equal to 0. And factoring by grouping works like this. You group, first off, you write the polynomial in descending order. This is the correct order, right? You start with the highest degree, 3, then 2. This is a degree 1, and this is degree 0, because it's a constant. And you might ask, well, how do I know if I'm going to use factoring by grouping? Well, typically, if you have a cubic polynomial and there are 4 terms, often it's set up like that for you so that you factor by grouping. So I group the first 2, and then I group the next 2 together. Okay, I factor them separately. So factoring this one, I have x squared is common to both of these terms, so I pull out the x squared. And if I factor out x squared from x cubed, I'm left with x. And if I pull out the x squared from this term, I'm left with 5. Then I go on to the next 2 terms, and notice they both have -25 as factors. So I pull out the -25. I'm left with x. And if I take negative 125 divided by negative 25, I'm left with plus 5. And because I'm factoring by grouping, it has to be true that these two are the same. If these do not match, then you've done something wrong, or you just simply can't factor by grouping. But so now the fact that this term and this term have a common factor of x plus 5, I can pull that common factor out. And I'm left with x squared minus 25. And the last step is to factor this difference of squares. And notice I have these two are the same factor, so I can write this as x plus 5 squared times x minus 5 equal to 0. So we have two zeros. If x plus 5 equals 0 from this factor, I subtract 5 from both sides and I get x equal negative 5. And then if I set x minus 5 equal to 0 and add 5 to both sides, I get x equal 5. So this is a real 0 with multiplicity 2, and this is a 0 with multiplicity 1, because that's just understood to be 1 there, okay? So plotting these, I get negative 5 and 5, and I'm going to pick test points. So I'm going to pick negative 6, 0, and 6. By the way, this is a square here, right? When you square a real number, it's always positive. So I don't really have to worry about this, what it's equal to. If I plug in negative 6, this becomes negative 11. I have a positive times negative 11. Is that greater than 0? False, right? If you have a positive number times a negative number, that's not greater than 0. So that region is false. When I plug in 0, I'm going to get positive times a negative. Wait a minute. And that, yeah, right? If I plug in 0, I get 5 squared, that's 25. Plug in 0 here, that's negative 5. So that's going to be negative 125. Is that greater than 0? False. And then finally, I'm plugging in 6. 6 minus 5 is positive, and this square is always positive. So that's going to be positive. True. Okay. So, when is this greater than 0? Well, this is the region. And you might be wondering, I'm surprised that we go false, false, because in all the other examples we went, it alternated, false, true, false, or true, false, true, whatever. So you may be wondering, why does it go false and then the next interval is false again? Well, the reason is because this 0 has multiplicity 2. And remember from a previous section, I think it was section 3.4, if you have a 0 that's multiplicity even multiplicity, it's going to touch the x-axis and then bounce back. So we're wondering, when is it greater than 0? Well, since it's false, that means it's below the x-axis and the function hits this spot, but then it bounces back because the multiplicity is even. And we'll look at the graph in just a moment, okay? So since we're strictly greater than 0, we're not including 5. So 5 to infinity, that's this region right here, is the solution set. Okay, from 5 to infinity. So let's take a look at the graph. And we have x cubed plus 5x squared minus 25x minus 125. And just as I had mentioned, you can see it's negative, and then right here it's 0, but then it's negative again. It doesn't become positive until this point right here at 5, and then it becomes positive, and it never goes negative again. So that's from 5 to infinity. So remember, the what is the height of the function. Here we see it's above the x-axis. Here we see it's below. The where are the x values. Where does it occur? Well, think of it as casting a shadow. The function is casting a shadow, and we're interested, when is it positive? So here it's positive. It's casting a shadow on this region here. And so that is where it's positive, from 5 to infinity. And notice I don't need a graph to solve this problem. A graph is helpful to understand, and you could use a graph to solve the problem, but I don't need, so this is the method you do it without a graph. Now we have a rational function. So the technique for solving these inequalities is very similar, but because you have vertical asymptotes, there's just one additional thing to consider. So in order to solve this, I want to find the zeros. So everything is on the left side of the equation. So in order for a rational function to equal 0, the numerator must equal 0. Okay, so x minus 3 equal to 0 will give me the 0. Because x minus 3 is the numerator. Okay. Now, in addition to having a 0 of 3, this is a rational function, so it has a vertical asymptote. So to find the vertical asymptote, you set the denominator equal to 0. And so in doing so, we get x minus 4 is equal to 0. And when you add 4 to both sides, you get x is equal to 4. So this is the vertical asymptote. And the function cannot equal 0, but it's possible for the function to change signs, have different signs on either side of the vertical asymptote. So that's a critical thing to look at. So when we plot, not only do we plot the zeros, but we also plot where the asymptotes are. So when I do this, I'm going to have 3 and 4 are, and I divide up my number line into 3 regions like this. This being the 0 and this being the location of the asymptote. And then I test my regions. So testing my regions, I get, I'm going to pick 0. I'll pick 3.5, and then I'll pick 5. So plugging in 0 into my original if x is 0, then I get -3 divided by -4. That's 3/4. Is 3/4 less than 0? That's false. It's not less than 0. Then picking 3.5, if I subtract 3, I get 1/2. If I subtract 4, I get -1/2, and so that becomes -1. Is -1 less than 0? True. And then finally, plugging in 5 here, 5 minus 3 is 2, 5 minus 4 is 1. 2 divided by 1, is that less than 0? That's false. 2 is not less than 0. Okay, now notice, oh, and I wish, let me check the problem. Hold on. I wanted it to say less than or equal to. Did I write that? Yeah. I'm going to change the problem if you don't mind, because I want to make a point here. I want to show you something. Let's pretend that the original problem said less than or equal, okay? The reason why I wanted to change the problem is because when you have a situation where it's less than or equal to, you have to be careful, because here we have a vertical asymptote. A vertical asymptote means that the function cannot equal 0 at that point. It's undefined, right? If I plug in 4 here in the denominator, that's going to give me 0. That's undefined. Dividing by 0 is undefined, so it's not equal to 0 here. So I'm going to use an open bracket on this side, but the function is equal to 0 at 3 because 3 is a 0. So I want to include that point. So you have a situation where on the left you include the point because this is a 0, and on the right here we don't include it because this is an asymptote. And that's because we're looking at the equal sign. Now, if I had left it as I had originally written it, this would have been without the, this would not have been square, this would have been open. But I wanted to make a point to show you that this is a possibility when you have rational functions, okay? So when I answer in Desmos, not Desmos, in MyLab Math, when I put the answer in, I'm going to put an open bracket because, but I just wanted to kind of show you that. So here, since it's less than, the solution set has open brackets. So from 3 to 4. But if it's equal, less than or equal, then I would have, made this square. Okay, and then the graph is right here. Okay, any questions on that one? So it's pretty much the same thing. You set the numerator equal to 0, you set the denominator equal 0. The only difference is you have to pay attention to where the vertical asymptote is. If you have something like this where you have less than or equal, then you want to leave out the vertical asymptote because it cannot equal 4 there, but you would include the 0, okay? All right, next problem. We're almost done here. We're getting to the end here. Why is it not letting, there it goes. Okay. So now this is an interesting problem because you'll notice that we're saying the rational function is less than or equal to 2. And if you're talking about where is it positive and where is it negative, this should be a 0, right? Because that's the change point where it goes from positive to negative. But what I'm going to do is, remember the first step of the problem was to move everything to the left-hand side. That's what I'm going to have to do here to fix that problem. So (8x minus 1 over 5x minus 2). I'm going to subtract 2 from both sides. And now it's going to have 0 on the right-hand side, which is what I want. but I want a rational function. This is a rational function, but I want a numerator over a denominator. So I have to combine these two. So this is going to be 8x minus 1 over 5x minus 2. And I'm subtracting 2 times 5x minus 2 over 5x minus 2. So this is 1, right? Multiplying by 1 still gives me negative 2. That's not going to change anything, but now I can combine these. And so when I combine them, I get negative 2 times 5x is negative 10x, and negative 2 times negative 2 is positive 4, and that's going to all be over 5x minus 2. We want to know, when is that less than or equal to 0? And then to simplify the numerator, I get negative 2x plus 3 over 5x minus 2. Okay. And so now we set each factor, or the numerator equal to 0. And we get x equals 3 halves. And then we set the denominator equal to 0. And we get x equal 2/5. Just verify that if you take 3 halves and plug it in, the 2's cancel, and I get negative 3 plus 3 is 0. Take the 2/5, plug it in, the 5's cancel, and then I get 2 minus 2 equals 0. So these are the correct solutions. Then I'm going to plot those on the number line. So 3 halves is 1 1/2, so that's going to be greater than 2/5, because that 2/5 is less than 1. And I'm going to pick, in my regions, I'm going to pick 0, then I'm going to pick 1, and then I'm going to pick 2. So plugging in 0 into my original, it becomes 1/2 minus 2. Is that less than or equal to 0? Yes, 1/2 minus 2 is less than or equal to 0. So that's going to be true. Then I plug in 1. 1 is going to give me 8 minus 1. That's 7. And 5 minus 2, that's 3. 7/3, is that less? Oh, wait, then I've got, hold on. What did I say? I said 7/3 minus 2. Well, 7/3 is 2 1/3. So if I subtract 2, that's going to be positive, right? So is that less than or equal to 0? That's false. And then plugging in 2, I'll get 15 in the numerator, 15/8. 16/8 is 2, so 15/8 is less than 2, and if I subtract 2, I'm going to get a negative number, so this is true. All right, and remember, this is an equal sign here, so the denominator, which is an asymptote, right here, this is an asymptote. That cannot equal 2/5. So when I'm trying to determine whether I include this point, I cannot include it. So I use an open parentheses. However, 3 halves, remember we set the numerator equal to 0 here. So that's a 0. So 3 halves is going to be included because we want to know, when is it less than or equal to 0. So 3 halves is going to be included. So the solution set goes from minus infinity to 2/5, not including 2/5, and then including 3 halves, and then from 3 halves to infinity, like that. That's my solution set. Let's take a look at the graph of this thing, because I think it'd be interesting to see how the asymptotes come into play here. So my function, my original function is 8x minus 1 divided by 5x minus 2. And sounds like a little kid in the hallway. Minus 2. And we're wondering, when is this less than or equal to 0? So I'm going to go ahead and graph the asymptote, the vertical asymptote, which is x. Remember, x equals 2/5. See, there's the asymptote. So we want to know, when is it less than or equal to 0? So you can see it's below the x-axis all along here and up until the asymptote, but you can't, it's not equal to 0 at the asymptote. So that's why we left that point out. But then it's above the x-axis, and I want to zoom in a little bit more here. It's above the x-axis on the positive side of the asymptote. And then until we get right here at this 0, now this is 3/2. Then it dips below. So the only place where it's greater than or equal to 0 is in this region right here to the right. I'm sorry, we're looking less than or equal to 0, where it's not, everywhere except this region is it less than or equal to 0. This is where it's positive. So everywhere else it's negative, and here it's equal to 0. So you can see we have it everywhere except that sliver in the middle there where it's false. It's not less than or equal to 0. It's above the x-axis in this region. So when you do these problems, take a look at the graph. It kind of gives you some insight into what's happening. All right, any questions on this one? We have maybe just enough time to do the last one, although I'll have to do it quickly. Like I said, if you don't get 100%, for those of you who are doing this online, if you don't get 100%, don't sweat it. I'll just give you full credit because I know this is a challenging problem. If you make a good faith effort, I'll give you full credit. All right, so this problem here, we're asked to find the domain of this function. So in order for this function to exist, the radicand, that's what's underneath, must be greater than or equal to 0. So we say 2x over x plus 6 minus 1 is greater than or equal to 0. And that defines the domain. And so this becomes 2x over x plus 6 minus, I should say minus, x plus 6 over x plus 6. And I'm going to distribute that minus to the negative, to the x and to the 6. So it becomes 2x minus 6 over x plus 6. When is that greater than or equal to 0? So that's x minus 6 over x plus 6. And we plot -6 and 6, right? Because if x minus 6 is equal to 0, then x is equal to 6. And if x plus 6 equals 0, then x is minus 6. So this is the asymptote because it comes from the denominator. This is the asymptote. And we want to know, when is it greater than or equal? So we're not going to include -6, but we will include 6 in our final answer. But first I got to pick test points. So 0, 7, minus 7. And plugging those in. Let's see, where do I want to plug them in? I guess I can plug them in here. Plugging in -7, I get a negative divided by negative. Is that positive? True. Plugging in 0, -6 divided by 6. Is that positive? That's false. Then plugging in 7. 7 is 1. 7 plus 6 is 13. 1/13. Yes, that's greater than or equal to 0. But because -6 is an asymptote, we don't include -6. So it's going to be an open, like a parentheses. But since 6 is a 0, and we want to know when is it greater than or equal to 0, we do include 6. And so the domain for this then is from -infinity to -6, not including not including -6, and then from 6 to infinity, including 6. So this is the D, the domain.